Hello. Today we are going to learn about quadcopters and how quadcopters fly. I will use today in this session small quadcopters. Okay, it works using the same principle for a big one. They are the same principle. We need to know some rules for flying quadcopters in order to be able to program even the simplest firmware for quadcopter. We are going to learn how quadcopters fly and what rules in physics they depend on in order to fly. First of all, we need to distinguish between quadcopters and helicopters. The main difference between them is that a multi-rotor and a helicopter, for multi-rotors it has two propellers, they are fixed pitch. For a helicopter, the propellers are variable pitch. Quadcopter specifically uses four propellers. They are in orthogonal configuration, okay, and these propellers are fixed pitch. Each propeller rotates in a certain direction, either clockwise or anti-clockwise. For example, this propeller moves anti-clockwise. This propeller moves anti-clockwise. Then this propeller moves clockwise. This propeller moves anti-clockwise. This propeller moves clockwise. Okay, let's draw it. For a quadcopter, we have four motors: M2, M3, M4. Suppose this goes clockwise, then this goes anti-clockwise, then clockwise, anti-clockwise. Another thing for quadcopter is that it has two famous flying configuration. It is either plus configuration or X configuration. X configuration is like that: M1, M2, M3, M4. The main difference between them is the following. For plus configuration, moving forward means moving in this direction. Moving left means moving in this direction. Moving right means moving in this direction. For plus configuration, we simply rotate the quadcopter 90 degree, 45 degree. So moving forward becomes in this direction. Moving right becomes in this direction, and moving left becomes in this direction. So this is the forward direction for X configuration, and this is the forward direction of plus configuration. From this figure, we cannot easily that plus configuration is the master one, because in this configuration, in the X configuration, these two motors together form a virtual motor here, VM1, and these two motors act as a virtual motor here, VM2, VM3, and VM4. So from now we will study, or we will explain our rules using the plus configuration. Let's start. The first thing we do when trying to fly with quadcopter is to give it some power, to give it thrust. If we raise here the thrust stick, motors will start to spin, and the much they spin, there is a power here, there is a force here that push quadcopter like that, or actually pulls quadcopter like that, and leaves the ground. So we want the quadcopter to be stable. So it makes sense that we need all the motors to produce the same force. So the force of the motor is proportional to the RPM of the propeller, or the RPM of the motor. For sure, it is not a linear relationship. It's not a linear relationship like that. But we can consider it linear, okay? Because the balancing algorithm, the balancing algorithm will adjust itself either it is linear or not. So we don't really care about what the curve is really, what is the type of the curve. Is it linear or curve like that or curve like that? It's not an issue here. So let's consider it for simplicity, it is linear. Okay. So that means we want the RPM of motor 1, RPM of motor 1 equals to RPM of motor 2 equals to RPM of motor 3 equals to RPM of motor 4, equal to a constant. This constant is determined by the thrust. It actually maybe is the value of the thrust, or the value of thrust, multiplied by a certain factor. But it directly depends on the thrust, and thrust only. Now let's consider that we give it thrust and the quad is flying now. Actually, without balancing, the quad will flip like that and it will never fly. It will never fly. It needs gyro at least to be able to fly. Because, why? Because there is no identical motors. There is nothing called identical objects, fully identical objects. You cannot say that this RPM is exactly the same as this RPM and they will produce the same thrust, and the CG is exactly here. You cannot say that, and you cannot even ignore outside the effects. Maybe some wind come from this direction. So without balancing, without using gyro, without active balancing, the quadcopter will not be able to fly at all. So the first thing, let's consider that we gave it thrust and now it is flying like that. And there is any external effect that push it in this direction. So what we need to do here is to increase the force that is generated by this motor by increasing the RPM, and decrease the force that is generated here by reducing the RPM. So when I push it like that, actually this motor will increase the RPM to give more thrust and to be able to balance it. Because without that, if I push it like that, it will just flip and actually will rotate. Okay? Because there is nothing will stop it from rotating. Okay? So when I push it like that, this motor will start to increase the RPM. So let's say, and here we come to the second rule. If we change M1 to M1 plus delta, we need to reduce M3 minus delta. Why? In order to keep this rule valid. Because without doing that, we will have other complication in yaw, and we will have complication here is that the total thrust is no longer the same. And we need to keep the thrust the same. So this is the first rule we need to remember. This is the second rule. Whenever we increase a motor, we need to decrease the other motor on the same axis. Okay? Now let's consider the third type of motion for quadcopter, which is the rotation in the yaw. When I change the rudder here, the quadcopter moves like that. And this is strange because the only force we have is a force that pushes this quadcopter vertically. So how can we achieve a force that, how can we produce a force that pushes this quadcopter like that and make it rotate? Okay, let's consider something. Let me hold this propeller, okay? Let me hold this propeller by hand and turn on the motor. Turn on motors. What will happen? If I leave the propeller will try to move, to rotate. But if I hold it, the quadcopter will try to rotate, but in the other direction. So if this propeller moves anti-clockwise, the quadcopter will try to move clockwise. So let's go back to this diagram. If I want the quadcopter to rotate, I can increase the RPM of motor 1 and motor 3 and decrease the RPM of motor 2 and motor 4. Let us study what will happen if I do that. Okay. M1 will become M1 plus delta. M3 will become M3 plus delta. And here the rule is different. And now M2 will become M2 minus delta. And M4 will become M4 minus delta. If we add this amount, we will find that the summation is M1 plus M2 plus M3 plus M4, and delta and all deltas are cancelled. Okay? And this returns us to the first rule. Here, M1, M2, M3, M4 are constant. Because when we increased by delta M1 and M3, we decreased by the same amount M2 and M4. So imagine a helicopter. Let's simplify this. Imagine a helicopter without a tail fan. What will happen? What will happen is that the helicopter plate, the main rotor will move like that. Let's assume it moves clockwise, and the helicopter will start to rotate anti-clockwise. The same effect happens here for quad. As I told you, if I hold this propeller, the quad will move in the opposite direction of the propeller. Actually, when I leave it in space, the quad wants to move in the opposite direction. But what happens? Because of this propeller moves opposite, rotates in opposite direction to this, so quad moves to rotate like that, and because of this propeller, the quad wants to rotate like that. So, as long as these motors are balanced, the quad is fixed and don't rotate, and doesn't rotate. Now, if we change the motors that affect the rotation in this direction, okay, by decrease the RPM here and increase the RPM here, we will find the overall effect is there is a force that makes this quadcopter wants to rotate like that. Okay? So let's review all these rules again. we said that there is a plus and there is X configuration, which is actually a plus because these two motors act as one virtual motor here. We said that M1, M2, M3, M4, the quite depends on the RPM of these motors. The RPM determined by the thrust. So M1 equals M2 equals M3 equals M4 is valid if we disregard or ignores the effect of balancing algorithm. This is valid, okay? And M1 plus M2 plus M3 plus M4 equal constant. That is determined by the thrust. And so this is the first rule. The second rule is for balancing the quad either in left, right, or front, rear. We use two motors on the same X. We use two motors on the same X. We will find that this motor, for example, rotates anti-clockwise, and this motor rotates anti-clockwise. So motors on the same X rotates in the same direction. So we can safely increase one of them, and we can safely decrease the other as long as we use the same amount for increase and decrease. Because if we violated this rule, the quad will start to rotate. So the third rule here, if we want to rotate the quad, we change the RPM of two motors by increase one X and decrease the other X of motors. For example, we will increase M1 by delta and M3 by delta and decrease M2 by delta, and M4 we will decrease it by delta. The first equation, we used it to generate the thrust for the quad. The second equation, we used it to balance the quad either in this direction or this direction. The third equation, we used it for balance the quad or make the quad rotate in this direction. As we can see here, we need to keep delta in the second rule in order to keep the torque from making the quad rotate for the third rule. So here we use plus and minus for the second rule to keep this the overall torque of the motors the same. The third rule here, we play with torque. We play with torque here. We increase the speed of motor 1 and motor 4 and decrease the speed of motor 3 and motor 2 and motor 4, and we increase the torque of the RPM of motor 1, motor 3, and decrease the RPM of motor 2 and motor 4, and that will generate more torque because of these motors than torques generated because of this motor. And that means if the propeller moves like that, if the propellers move like that in clockwise, the quadcopter will try to move anti-clockwise. See here, I hold the two propellers, and they are, as you can see, it is fixed, and the quad tries to move in the other direction. Okay. Okay. I want to thank you. In other sessions, I will go in how to determine this delta using PID, and I will talk about some sensors that we will use in order to determine this delta. Thank you very much.